So welcome. Let us draw the waveform for three-phase 12 pulse converter. So we have two voltage waveforms here. This is a set of three-phase voltages. Here it is written line voltage. Instead of writing the line voltage, we can write VY. VY means star. This is the output voltage of star connected transformer. That is this. This is our star connected transformer, and input voltage to our this converter is this VY. We call this VY, star connected, output voltage of star connected transformer secondary. And converter C2 is excited by this delta connected transformer. So its voltage we can write as V delta. So this voltage here, it is written phase voltage. We will not write phase voltage, we will write V delta. And they already have 30 degrees phase displacement. So let us complete this omega. Let us draw this omega t axis. For both, this is omega t. So I will write here three-phase 12 pulse converter, and we will draw the waveforms for rectification mode. Let alpha be equal to 15 degrees and u be equal to 0 degree. We will not consider any commutation overlap here. Now this is our star output voltage of star connected transformer secondary, which is fed to converter C1. Here I will write converter C1, and this is the output voltage of transformer secondary, which is delta connected, and this voltage is fed to second converter C2. Okay, now let us label the voltages, commutation voltages. So as usual, our first voltage is commutation voltage of value 3, EBA. EBA is followed by ECA, then ECB, we already know it, then EAB, then EAC, then EBC, then EBA again, right? And what about bottom waveform? In the bottom waveform, see, this is, what is this wave? This wave, you can see it is EBC. So this is EBC. By the way, this is the commutation voltage of value 3, and this is reference for firing of value 3. So here I will write omega t equal to 0 degree. And here EBA is 0, means EBA, I will write here, EBA will be equal to 0, which means EBA is equal to EB minus EA is 0, which means EB is equal to EA. So therefore here omega t is equal to 0 means if you go down, it coincides with this point. So that means this will be your EB, and of course this will be your EA. We have already, on number of occasions we have established this. So this gives you first voltage waveform, EB. EB will be followed by, after 120 degrees, that means isko chhod ke next jo aayegi, that is EC. Then after 120 degrees, leave this is EA. So this is EB. After 120 degrees, peak of EC comes, and after 120 degrees, peak of EA comes. So if this is EB positive, it's negative voltage. This will be minus EB. So this is minus EB. If this is plus EC, you can see this is plus EC. Aap idhar jaiye. This is minus EC on this side, and this is minus EC on this side. Similarly, if this is plus EA, you can see this is plus EA. Its phase reversed voltage is minus EA on this side, and you go on this side, it's minus EA here. What is this? So this is minus EB, iski mirror image hai, so this is plus EB. So this completes our labeling of the two waveforms. Let us start with the conduction of, with drawing the waveform of converter C1, okay? And here is your converter C1. You can see converter C1's output voltage is VD1. Here I have written VD1, okay? We'll start with the firing of value 3, and already we have the firing table or conduction table. 2-3 pair is conducting, and alpha is equal to, you have already written here, alpha is 15 degrees. This is omega t equal to 0, and after 15 degrees, यहाँ से यहाँ तक आपका यहाँ से यहाँ तक आपका 30 डिग्रीज है। ओके, यहाँ से यहाँ तक 30 डिग्रीज है, 15 डिग्रीज इसका सेंटर होगा। सो दिस इज 15 डिग्रीज। सो दिस इज योर अल्फा इक्वल टू 15 degrees, because you have assumed alpha very small, 15 degrees. So from this crossover to this crossover, we already know these are 30-degree crossover points. So half of it is 15 degrees. So this is alpha equal to 15 degrees. And after a delay of 15 degrees, which value is fired? Value 3 is fired. Then once you know the firing instant of value 3, you can symmetrically find the firing instant of value other values after 60-degree interval. 60-degree interval means यहाँ से यहाँ तक ये 60-degree interval. This is value 4 will be fired here. So value 4 will be fired here. Then here after 60 degrees interval, value 5 will be fired. Then value 6 will be fired. Then value 1 will be fired. Then value 2 will be fired, and finally we will go back to value 3 and another cycle will start. Okay, so when value 3 is fired here, this gives 2 3 conduction, then 3 4 pair will conduct, 4 5 5 6 6 1 1 2 and 2 3 again. Right now, when value 3 is fired, you have 2 3 conduction, and with 2 3 conduction, here is your conduction table. When 2 3 pair is conducting from 15 degrees to 75 degrees for 60 degrees, what is your load voltage? It is EBC. And where is your EBC? Just go up. This is here, 3 is fired, and it gives for 60 degrees 2 3 pair is conducting, and your load voltage is EBC. ये ऊपर आपकी EBC है. First you take all these firing instants up. आप ये ऊपर ले जाइए. Take all these firing instants up. Okay, now my load voltage for 60-degree interval is EBC. Let me shade this EBC. Okay, fine. Then value 4 is fired, and our conduction changes from 2 3 to 3 4. And when 3 4 pair is conducting, what is your load voltage? You can see here, when 3 4 pair is conducting, this is 3 4 pair, your load voltage is EBA. Here is your EBA, load voltage. And where is EBA? Just above it. It will jump a little bit and it will follow EBA till next instant of firing. That means for entire 60-degree period, your load voltage is EBA. After this, you don't need to see the table. You just follow this pattern. This is your first voltage segment, EBC. Next voltage segment is EBA for 60 degrees. Next voltage segment symmetrically will be, identically, it will be ECA for next 60 degrees. Next load voltage segment will be ECB. Just follow this pattern. Next will be EAB. Next will be EAC. And you are back to EBC. So this is load voltage waveform. I will write here, this is VD1, voltage waveform, voltage output of converter C1. Okay, you can see we are considering converter C1 and its voltage is VD1, and we have drawn, this is the output voltage of converter C1 for alpha equal to 15 degrees and U equal to 0 degree. No commutation overlap is there. Your load voltage with the firing of value 3, when 2 3 pair is conducting, as here, your load voltage is EBC. It's for 60 degrees, it's followed by EBA for next 60 degrees, and so on. ECA, ECB, EAB, EAC, so on. So this is load voltage produced by converter C1. That is, this is VD1. What about second converter? Second converter is fed by delta, and its voltage is V delta. I have written input voltage of second converter is E delta. It is fed by delta connected transformer secondary, and these are the voltages, various voltage waveforms. Now, what is the commutation? See, here we have started with the commutation of value 3. And what is the commutation voltage of value 3? It is EBA. Or when I say alpha is 15 degrees, आप यहाँ से यहाँ from omega t equal to 0 to यहाँ से यहाँ तक, alpha is 15 degrees and you fire value 3. And in the converter C2, what is the commutation voltage of value 3? Yeah, you have already drawn that on whiteboard and I am reproducing that. This is converter to commutation voltage. Value 3 key commutation voltage, you can see it is minus EA. Just search where is minus EA. in the waveform. This is minus EA. और इस minus EA का zero crossing ये है. So this is omega t equal to 0 for second converter. Okay. So it's the commutation voltage of value 3 is EA minus EA. So that is this. Omega t is equal to 0. So use and alpha is same. Alpha is 15 degrees. तो यहाँ से यहाँ तक इस crossover से इस crossover तक 30 degrees है. 15 degrees बीच में है. So that means after a delay of alpha electrical degrees, so here alpha is equal to 15 degrees, value 3 is fired. तो यहाँ value 3 fire होगा. And then symmetrically after 60 degrees, ये आपका next 60 degree interval है. After 60 degrees, this is value 3 dash is fired here, value 4 dash will be fired. Then after next 60 degrees, value 5 dash will be fired. After next 60 degrees, value 6 dash will be fired. After next 60 degrees, 1 dash. Then after 60 degrees, 2 dash. And after next 60 degrees, 3 dash will be fired again and cycle will repeat. So with the firing of value 3 dash, what is the pair of values which will be conducting? 2 dash, 3 dash. With the firing of value 4 dash, 3 dash, 4 dash pair will conduct. And then for next 60 degrees, 4 dash, 5 dash pair will conduct. Then 5 dash, 6 dash. Then 6 dash, 1 dash. Then 1 dash, 2 dash. And then again 2 dash, 3 dash. Cycle repeats. Now let's see the voltages. Here is your table. You need this table again and again. And this is your converter C2, this conduction table. When 2 dash 3 dash pair is conducting for 60 degrees from 15 degrees to 75 degrees, what is load voltage VD2? It is EBB dash, that is, it is EB. Search EB. What is EB? आप देखिए here value 3 is fired, and when 2 dash 3 dash pair is conducting, your load voltage is EB. EB ये है आपकी. So let us take this firing instance up. It will help us in identifying the voltage segments. So your load voltage for this 2 dash 3 dash pair value pair conduction for 60 degrees is EB. So this is EB. So at this instant value 4 dash is fired, and your value pair changes from 2 dash 3 dash to 3 dash 4 dash. When 3 dash 4 dash pair is conducting, what is load voltage? See, this is 3 dash 4 dash pair, and load voltage is minus EA. You can see it is minus EA. Why it is minus EA? Just इसके ऊपर minus EA. So it will go up till next instant of firing. Your load voltage will be minus EA. And after this, you don't need to see the table. You identically follow these segments. Your first voltage segment is EB. Next voltage segment is minus EA. And next voltage segment will be EC. Next voltage segment will be minus EB. Next voltage segment will be EA. Then it will be minus EC. And then again EB. So this is the load voltage of, this is load voltage, I should write here VD2. Load voltage produced by second converter, VD2, which is converter, 6 pulse converter, which is fed by delta connected secondary, and its output voltage is VD2. So you can see it is VD2. So we have drawn. Now what is your total load voltage? Your total load voltage is, I can write your net load voltage, VD is equal to VD1 plus VD2. So you need to add these two voltages. It is interesting to see that when you add the two voltages, आप देखिए यहाँ से यहाँ तक, you have to identify these segments. फिर ये next segment है, ये आपका next segment है. So you will get, from this to this, यहाँ से यहाँ तक, this is VD1 and this is VD2 will be somewhere here. ये आपकी VD2 है. Somewhere this is your VD2. So add the two voltages, you will get first voltage segment like this. उसके बाद ये next segment है, उसके बाद ये next segment है, उसमें VD1 ये है और VD2 ये है. When you add the two voltages, you will get next segment. So you continue like that. Let me first of all complete these segments, and देखिए, this is first voltage segment, load voltage. This is your total voltage, load voltage, VD, which is equal to VD1 plus VD2. When you add this first voltage segment, second load voltage segment, third, fourth. I'm drawing roughly 5. You can draw it properly at your homes, at your residences. 6, 7, 8, 9, 10, 11 and 12. So you'll get 12 voltage segments. That means if you take one cycle of AC, for one cycle of AC, how many voltage segments you get at output? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's why it's called 12 pulse converter. So 12 pulse output voltage, VD. So you just, it's very simple. You have to add the two voltages at different instants. You will get this voltage plus this voltage, this voltage plus this voltage, this voltage plus this voltage over these different instants. This will give you net output voltage, which is impressed across the load, VD, which is equal to VD1 plus VD2, and it's a 12 pulse voltage. Fine. Now our next mission is to find the line current. Let us try to find line. So see, we have three line currents. We have line current IA, this line current IB, this is line current IC. Similarly here, line current IA, IB and IC. Let us take line current IB. Okay. Now you can see from the converter configuration, this IB will be equal to plus ID when 3 is conducting. See, when 3 is conducting, current will come out, it will flow through 3 and it will go into the load. So ID is equal to, so I will write here ID, yes, IB. This is your IB. देखिए ये आपकी IB है. This is IB. IB will be equal to plus ID when value 3 is on, when value 3 conducts. So value 3 जब conduct करेगा, your phase B is connected to value 3. When value 3 conducts, IB will be simply equal to ID. That's what I have written. And when जब इसका नीचे वाला conduct complementary value 6 conduct करेगा, then current cannot flow from cathode to anode. It has to come from anode to cathode. Current इस तरह आएगी and it will go. यहाँ से load current ही, in fact ID ही आएगी. ID will enter. It will flow through 6 and it will flow into the phase, but in opposite direction. So IB will be equal to minus ID when its complementary value 6 is conducting. When value 6 conducts. So that means, see, phase IB or line IB is connected to middle leg, and in the middle leg comprises of upper value 3 and lower value 6. When upper value 3 is conducting, IB is equal to plus ID, and when lower value 6 is conducting, current flows from anode to cathode, IB is equal to minus ID. That's what I have written here. IB is equal to plus ID when value 3 conducts, and it is equal to minus ID when value 6 conducts. With this in mind, let us see. आप यहाँ देखिए, 3 is conducting over this 60-degree interval. 2-3 pair is conducting, so 3 is on. Then 3-4 pair in next 60-degree interval is conducting. You can see. So 3 is on for this 60-degree interval and next 60-degree. Total is 120-degree interval. तो यहाँ से यहाँ तक 3 on है. यहाँ से यहाँ तक. So your load, your phase voltage, your phase B voltage or line B voltage will be equal to, this is your line voltage IB, and it is equal to plus ID over this 60 plus 60, 120 degrees, because over this 120 degrees value 3 is continuously conducting, and when value 3 is conducting, your load voltage is plus ID. A few moments back we have established it. After this 4, 5 is conducting. That means none of the, neither 3 is conducting nor 6 is conducting. 4, 5 is conducting. 4, 5 is conducting. That means your line current IB becomes 0 for next 60 degree. उसके बाद 5, 6 and 6, 1. That means 6 is conducting over this 60-degree interval and this 60-degree interval. यहाँ से यहाँ तक 6 conduct कर रहा है. And we already know when 6 is conducting. See, when value 6 is conducting, what is your load voltage? It is minus ID. So it will go down, and it will be minus ID from here to here. So it will be minus ID. So this is your line current IB. Okay, similarly you can draw line current IA, IC. They will be similar, plus 120 degree ID and minus 120 degree period ID, but they will be phase displaced with respect to each other by 120 degrees. This is for converter C1. What about phase line current IB in converter C2? Now this is our converter C2. इसमें भी हम line current IB find करना चाहते हैं. So you cannot find it like this. You have to make some, some equivalent circuits you have to draw. Okay. Let us start with 2-3- conduction. I will use another paper. Let us start with the finding of value 3- in the lower converter. It gives 2-3- value conduction. So go to the converter. 2- means ये value आपका on है, and 3- means ये value on है. And let us draw the equivalent circuit on this sheet. Equivalent converter circuit of lower converter C2. उसका equivalent circuit, it will look like this. Let me draw first, then I will explain. This is your delta connected transformer, secondary. This is A', B, B', C, C'. Now we can see from here 3- and 2- are conducting. 3 is conducting, that means यहाँ से 3 conduct कर रहा है. So 3 is on. So I will show 3 like this. 3- is on. And this is LD, and this is your load current ID. और ये आपका load है. Bottom value में कौन सा value on है? 2 is on. So जब यहाँ से load current ID आएगी, it will flow through 2- and back to this B'. 2- is on. It will 2-, 3-, it will come here. ये open है आपका. So you again try to understand this. 2-3 pair of valves is conducting. 3- is conducting. That means 3- आपके साथ इसके साथ connected है. So current ID will flow like this through 3-, then it will flow through load और यहाँ से वापस आएगी, and then through 2- it will go back. So using this, I have drawn the equivalent circuit. Now you see this is current ID. It comes out and it enters here. यहाँ ये enter हो जाती है. जब current यहाँ enter हो जाती है, it finds 2 paths. Some current flows here and some current flows here. Now the question is, how much current will flow in these two? ये दो series में आ जाएंगे. और how much current will flow in this? Let us assume this has an impedance Z. All the 3 phases have same impedance. So when current enters this, ये दो series में है. Use current divider formula. What is current in this branch? Current in this branch is impedance of opposite branch. Opposite branch में ये दो series है. What is total impedance? 2Z divided by total impedance Z plus Z plus Z, 3Z, into what is total current entering. It is ID. So Z or Z cancel हो जाएगा. So this is 2/3 ID. That means current which goes down here, it is 2/3 ID. So if this is 2/3 ID, what is current going here? It is 1/3. यहाँ 1/3 ID होगी इन दो branches में. So it is 2/3 ID here, 1/3 ID here. So therefore आप देख सकते हैं current, I am interested in finding IB current. ये IB है, ये मेरा phase IB है. So therefore phase B में current B' से B की तरफ flow हो रही है. So I get current IB', that is equal to minus IB. And what is that equal to? That is equal to minus 2/3 ID. Okay. So this is it. Now ये तो हो गया when 2-, 3- pair is conducting. Now what about 2-, 3- के बाद 3-, 4- pair conduct कर रही है. Let me draw equivalent circuit for 3-, 4- again. This is A', B, B', C, C'. Now go to this. 3-, 4- is conducting. 3- conduct कर रहा है, तो ये circuit 3- conduct कर रहा है. So I will write 3- is conducting. As in the previous case, it was conducting load current ID, and that current is flowing through the load. Now here return path is not provided by 2-. Here return path was provided by 2-. Here return path is provided by 4-. What is 4-? You can see जब current यहाँ से आएगी, instead of flowing through 2-, it will flow through 4-. और 4- इस terminal के साथ connected है. So it will flow through 4-. और 4- किस terminal के साथ connected है? Just check. A के साथ. It is connected to this. So that means return current is like this ID. और जब ये आईडी इसमें एंटर हो जाएगी ये फिर से स्प्लिट हो जाएगी, इन दो में सेम करंट फ्लो होगी, इसमें ये करंट फ्लो होगी। ओके, अब ये what will be this current? As usual this will be 2/3 ID, and what will be this current? This will be 1/3 ID. Since current is flowing from B dash to B, so your IB will be equal to minus 1/3 ID, right? This is 3 dash 4 dash. Then 4 dash 5 dash pair jab conduct karegi, next pair, let us draw the equivalent circuit. This is A dash, B dash, C dash. Okay, 4 dash, 5 dash. So 5 dash is now conducting. You can say 5 dash is conducting. It is connected to this phase. It's connected to B dash. तो B dash से एक लाइन आएगी और 5 dash conduct कर रहा है ये load के साथ. So it conducts load current ID. So this is your load. Return path is provided by 4 dash as in the previous case. Previous case में भी 4 dash. तो ये 4 dash will provide return path and it will get connected here. तो अब now current ID is coming out, it is flowing through the load और यहाँ से वापस enter हो रही है. When it enters, ये दो अब आप देख सकते हैं ये दो अब सीरीज में आ गए, because some current gets flows in these two branches are in series and some current flows here. ठीक है, अब इन दो branches में current flow हो रही है. So what is this current? This current will be plus 1/3 ID and this will be 2/3 ID. But now current is flowing from dot to undot. Previously it was flowing from undot to dot, B dash to B. So it was taken as minus ID. Now it is flowing from B to B dash, that is dot to undot. You have to take it positive. So IB is equal to plus 1/3 ID. Right? 4 dash 5 dash के बाद 5 dash 6 dash pair conduct कर रही है. Let's draw the equivalent circuit again. So this is A dash, B dash and C dash. 5 dash अभी भी conduct कर रहा है, 5 dash यहाँ भी conduct कर रहा था, यहाँ भी conduct कर रहा था. So ये terminal 5 dash से आएगा and load current ID will be flowing and this is load. Now return path will not be provided by 4 dash, it will be provided by 6 dash. What is 6 dash? आप देख सकते हैं, this is your 6 dash. So when current enters, it flows through 6 dash और 6 dash कहाँ पे connected है? 6 dash is connected to this junction. So this is your 6 dash और 6 dash किस junction के साथ connected है? You can see 6 dash is connected to A dash और B junction here, this. तो इसका मतलब करंट अब एंटर हो जाएगी ऐसे. जब करंट ऐसे एंटर हो जाएगी, सम करंट विल फ्लो हियर और ये दो अब सीरीज में आ गए. अब व्हाट इज दिस करंट? दिस इज प्लस 2/3 ID. सो देयरफॉर एंड करंट इज फ्लोइंग फ्रॉम डॉट टू अनडॉट, दैट इज B to B dash. सो देयरफॉर IB इज इक्वल टू प्लस 2/3 ID. सो 5 dash 6 dash के बाद 6 dash 1 dash आएगा, उसके बाद 1 dash 2 dash आएगा, उसके बाद 2 dash 3 dash फिर से आएगा. So if you continue like this, see we started with 2 dash 3 dash. For 2 dash 3 dash, we found that phase current or line current was minus 2/3 ID. You can see here minus 2/3 ID. This was the phase current IB. 3 dash 4 dash के लिए what was the load? What was the phase B current? 3 dash 4 dash pair के लिए here it was minus 1/3 ID. Minus 1/3 I will write here. 4 dash 5 dash pair के लिए अभी हमने थोड़ी देर पहले निकाला. What was IB? IB was plus 1/3 ID. Plus 1/3 ID. 5 dash 6 dash also we just few moments back we found for 5 dash 6 dash IB is plus 2/3 ID. So this is plus 2/3 ID. If you continue like this 6 dash 1 dash के लिए फिर से 1/3 plus 1/3 ID हो जाएगी और 1 dash 2 dash के लिए ये minus 1/3 ID हो जाएगी and you can continue like this. ये वापस जाएगा 2 dash 3 dash minus. So minus 2/3 ID, minus 1/3 ID, plus 1/3 ID, plus 2/3 ID, plus 1/3 ID, minus 1/3 ID. And with this, we can show it on the waveform sheet. Okay. Now, we started with 2 dash 3 dash. When 2 dash 3 dash pair was conducting, when 2-3- pair was conducted, what was your load current for 60 degrees? Your phase B line current. It was -2/3 ID. आप यहाँ देख लीजिए. 2-3- pair is conducting during this 60-degree interval, and during this 60-degree interval, my phase current IB is -2/3 ID. Let me use red color pen. It is this -2/3 ID. This is my line current IB. Okay, fine. Uske baad, when 3-4- pair is conducting, what is my line current IB? It is -1/3 ID. 3-4- is conducting for this 60 degrees. You can see. So ये drop हो जाएगी from -2/3 ID to -1/3 ID. So this is your -1/3 ID, right? उसके बाद for next 60-degree interval, when 4-5- pair is conducting, it goes from -1/3 ID to +1/3 ID. So for next 60-degree interval for 4-5- conduct, it goes from -1/3 ID to +1/3 ID. So this is plus ID by 3 or +1/3 ID. Then for 5-6- pair, it goes from +1/3 ID to +2/3 ID. So it goes from +1/2 ID to +2/3 ID. ये increase हो जाएगी. It will increase by one step. So this is 2/3 ID. You continue like this. It will come back to 1/3 ID, then -1/3 ID, and so on. So this is phase B current or line B current. This is the line B current for converter C1. This is the line B current for converter C2. What is total line current? If you see total line current drawn by primary winding of transformer, this is the primary winding of transformer. This is total line current IB. It is equal to IB plus IB dash. I mean, if you call this IB, this is IB, and you can call this IB dash. You can call this IB dash. Let's go up IB dash. So the current in transformer primary, current drawn by transformer primary in line B, that is IB, capital B, is IB plus IB dash, where IB is this current and IB dash is this current. Okay, sum of the two currents. And if you sum them up, your IB is, see, it is a Cauchy square wave or Cauchy rectangular, and this is a stepped waveform. At each and every, in each 60-degree intervals, you have to add them, because your total current in the transformer primary is this current plus this current at each instant. And if you add them up, you will get net ID like this. Let me show you. You can try this at your home. 1, 2, you will get 3 steps in positive half cycle and 3 steps in the negative half cycle. So this is your IB, current in the transformer, current drawn by converter from the primary winding from source. This is IB plus IB dash. So you can see it is stepped waveform, and it is, closer to sinusoidal. As the number of steps increases, your current approximates a sinusoidal waveform, right? So therefore, for 12 pulse converter, your line current IB is stepped. It approximates a sinusoidal waveform. Similarly, IA and IB, IA and IC will be similar, but 120-degree phase displaced. If you go from 12 pulse converter to 24 pulse converter, number of steps in the line currents will further increase from 3 to 6, and current will be more closer to sine wave. So that means the distortion level in the current drawn by converter from the source further reduces. And I have already told you the harmonic order in a 12 pulse converter or in a 6 pulse converter is given by this relation, NP plus minus 1, where P is pulse number, P is called pulse number, and N is an integer. And integer means it's any integer, 1, 2, 3, 4, and so on. So therefore, for 12 pulse converter, what are the harmonics that are present? For 12 pulse converter, P is equal to 12 and N is equal to 1, 2, 3, and so on. So substitute N equal to 1 and P equal to 12. 12 minus 1 is 11 and 12 plus 1 is 13. So P is 12 and substitute N equal to 2. 2 12 are 24. 24 minus 1 is 23. 24 plus 1 is 25. Substitute N equal to 3. 3 12 are 36. 36 minus 1 is 35. And 37. So these are the harmonics which are present in the current drawn by converter from the source. The harmonics. And for 6 pulse converter, if you remember, for 6 pulse converter, H is equal to NP plus minus 1, and there P is equal to 6 and N is equal to 1, 2, 3 and so on. And harmonics which are present in the line current are P equal to 6, N equal to 1. 6 minus 1 is 5, 6 plus 1 is 7, then 11, 13 and 17, 19 and so on. So the most predominant harmonic in a 6 pulse converter is 5th, lower order harmonic, followed by 7th, followed by 11th and so on. And in a 12 pulse converter, there is no 5th harmonic component in the current, there is no 7th harmonic component. The most predominant harmonic is 11th, followed by 13th. Then there is no, you can say in 6 pulse converter you have 17 and 19 harmonic components. There is no 17 and 9, and from 13 direct 23 and 25. So therefore there is a drastic reduction in the harmonic content in the current. Therefore, if you draw the harmonic spectrum of line current, you can draw the harmonic spectrum of current like this. This is the harmonic order H. And if you remember, we have already done in previous lectures, this is IH by I1. IH is the harmonic current as a ratio of fundamental component of current. For harmonic equal to 1.0, that means for fundamental, there will be this IH by I1 will be 1.0. That means fundamental component is 100% there. Then there is no 5th harmonic, no 7th harmonic, which is the most predominant harmonic, 11th. So you will start from here. 11th harmonic, this is 11th harmonic and its amplitude is 1 by 11. 11th harmonic is followed by 13th harmonic, whose amplitude is this. This is 13th harmonic with amplitude 1 by 13. There is no 17th harmonic, no 19th. Next is 23rd harmonic. So it is somewhere here. Its amplitude is very, very small, 1 by 23. And next is 25th harmonic, negligible small. 25th harmonic has an amplitude 1 by 25 and so on. And this is the harmonic spectrum of line current. You can see 5th, lower order harmonics, 5th and 7th are completely absent. So 11th and 13th harmonics are there, and 17th and 19th harmonics are also absent. Therefore, higher order harmonics only are present here. And if you need harmonic to remove these harmonics, 11th and 13th, you need 2 single tune filters. One tuned to 11th harmonic, which will suppress 11th harmonic component of line current, and another 13th tuned to 13th harmonic. It will remove 13th harmonic component of the current. And for higher order harmonic, you need a small band pass filter. For 6 pulse converter, you need at least 4 tuned harmonic filters. One tuned to 5th harmonic, one to 7th harmonic, one 11th, one 13th, and then a high pass filter. So here you need at least 4 single tune filters. Here you need only 2 single tune filters. So suppressing the harmonics is very, very easy in 12 pulse converter, because harmonic spectrum of line current is much better than harmonic spectrum of line current in a 6 pulse converter. So the size of filters, the cost of filters required, harmonic filters required in 12 pulse converter is very, very small. Cost is very low. So this offers advantage of 12 pulse converter over 6 pulse converter. So 2 advantages. Number 1, we have a 12 pulse converter. As you know, one of the main requirements or desirable features of a converter which we should use for HVDC transmission purposes is that pulse number should be as high as possible. 12 pulse converter has a pulse number of 12, so whereas 6 pulse converter has a pulse number of 6. So that means 12 pulse converter is preferable over 6 pulse converter. So output voltage and output current, load current or line current has very small ripple. And second is the harmonic spectrum of current is much better than that of a 6 pulse converter, because there is no 5th harmonic, no 7th harmonic. The most predominant harmonic is 11th and followed by 13th, and it is easy to filter out 11th and 13th harmonic rather than filtering out 5th and 7th harmonics. So you can use only 2 single tune filters for filtering out and the line current drawn by the converter will be almost purely sinusoidal. So it is because of this that 12 pulse converter is very popular for HVDC applications. So summarizing what we have learned in today's lecture is that we first discussed 12 pulse operation of converter. A 12 pulse converter comprises of 2 6 pulse converters connected like this. One is excited by Y connected transformer secondary and another by delta connected transformer secondary. The AC input voltages are phase displaced by 30 degrees. And when we consider the load voltage waveforms VD1 and VD2 of the two converters, they look like this. This is VD1 for converter C1 and this is VD2 for converter C2, and total load voltage VD is equal to VD1 plus VD2. It is this, and it is a 12 pulse voltage output. And then we have also drawn a waveform for line current IB for both the converters IB and IB dash. And if you add the two line currents, your total line current drawn by converter from the transformer, from the supply, is like this. So this has a better harmonic spectrum than the current drawn by a 6-pulse converter. And this is the harmonic spectrum of line current. So 12-pulse converter is advantageous over 6-pulse converter for HVDC applications on two accounts. Number one, the number of pulses is double than the number of pulses. The here pulse number is 12, whereas for 6-pulse converter it is only 6. And secondly, the line currents drawn by converter from the source are having better harmonic spectrum, and it is easy to filter them out and make them sinusoidal currents. So I will end my today's lecture. I advise all of you to go through this lecture, try to draw converter these waveforms yourself, and try to draw in addition to these load voltage waveforms, and try to draw line current waveform. Here I have drawn for line current IB. You can try for IA or IC, and draw the harmonic spectrum, total line current, which is this, and harmonic spectrum. So go through it. In case of any difficulty, you can ask me the queries. You are most welcome. So with this, I will end my today's lecture. Thank you.